Okay, so here's question 1. Question 1 in 4.2. Okay, so basically they have these, they're giving these as percentages, but you don't need to worry about it. Don't do anything different. Just do the regular, it'll all be good. What does that mean? Well, let's find the standard divisor first off. What's the formula for standard divisor? Total population over number of seats, huh? Okay. So the number of seats is right there, 500. That's clear. What's the total population, though?
100.
Yeah, how'd you know that? Yeah, good job, good job. Yeah. Yeah, notice they're not, normally they give us like a total thing over here, don't they? And they have like a total for us, and we just grab it. They're not giving us total. So if we add all these up, we'll get the total, and guess what it'll be? 100, because it's percentage. So of course, yeah. So it's just, I'm just letting you know, this is just 100. So good job, exactly right. It's 100% on that. So we're just talking percentages. Anyway, it's just kind of weird. They're doing percentage. Divide that to 0.2, right? Yeah, 0.2. So that's right here, standard divisor, 0.2. Don't worry about the percentage. You don't got to move decimals at all. Don't let that throw you off. It's kind of weird. It's kind of a strange one, so I wanted to show it to you. It's weird that they're using percentages, but anyway, you can completely ignore the fact that they're using percentages and do everything regular, and it'll all be fine. So if you just add these numbers up, it indeed comes out to 100. If you do the standard divisor calculation, it indeed is 0.2, just like we thought. Okay, and then how do you get the quota for A? Maybe we'll do one of them and go to the next problem. How do you get the quota for a state? You take the population for that state over the divisor, right? So that'd be, what's population for A right here? 6.89 over the divisor, 0.2. And I'm assuming you get that number right there. 9 divided by 0.2. Yep, 34.45. Right there. There it is. So is that good? I'm just going to skip. They don't even have us do a method on this one. They don't even have us do Hamilton, Jefferson, Adams, or Webster. All they do is just have us do these 4 divisions. And we're done. So I'm going to move on to problem 2, if that's okay. Nothing. So I just wanted you to, I wanted to make sure you weren't thrown off by percentages. You can completely ignore them and just do everything regular. And that problem works out fine. So there we go. Number 2, Hamilton's. Okay. So one thing they're not giving you that you need is the total out here, right? We need that total. So let's add that up and get that total. 875, 1,002, 625, 690. 3192 is what I'm getting. 3192. Okay, so take it from there. They want you to do this whole problem with Hamilton's, you see it out here, Hamilton's method, and figure out, and there's the answers already there for you, but see if you can get those answers see if you remember Hamilton's method. So you got to go through, and I'm going to bring it down here. You got to form the divisor, so you got to take the 875. Oh, you got to find the standard divisor first, that's right. So you got to find the standard divisor, and that's always total population over number of seats. So total population, that's the 3192. Number of seats, 228 nurses. So we're distributing nurses to different shifts in the hospital. So 3192 divided by 228, 14. So divide all these numbers by 14. 14 is the standard divisor. Yeah, so they're using this to figure out how the nurses should be broken up over various shifts depending on how many patients are needing their services in the various shifts. So divide by those. So divide them all by 14. So get those numbers, if you can get those on your calculator, and do the Hamilton thing. See if you remember what that is. I'm going to go, I think I have a handout for you on this section. Let me go check it in my office real quick. Remember. That's you.
Thank you.
don't have a handout, so I'm just thinking of another chapter, I guess. All right, so let's crank these out. And then you round them all down, right? And give the extra seats. You round them down, add them up, give the extra seats to the highest decimals. That's Hamilton. Just want to make sure you remember Hamilton. 71.6. 44 point. Oh, I better be more accurate. This is 6.4. What was the last one? I need more accuracy. It was 5.7 really, so it's a little bit lower. Oh, what was the? I guess I should be going 2 decimal places. Go back to this is 5.0. Okay, and 690 divided by 14. This is 49.29. So I guess I need 2 places. Okay. So anyway, Hamilton says Hamilton round down. So round them all down at first. 62, 71, 44, 49, right? At first. Add them up. See how many seats you got. Give the extras to the highest decimals. What do we got there? 3, 7, 6. Oh, some kind of 6. Oh, we're way off, aren't we? I'm getting a 6 in the units place. Does that mean it's 686?
It's 626, so we're 2 off.
Oh, yeah, I forgot. Yeah, I'm looking at the wrong number. Yeah, thanks. 226, right. So we're off by 2. Yeah, we're supposed to have 228 total. So 2 more, right? Because 228 is the number. We're 228 nurses we have to pass out in the various shifts. So there's 2 more needed. Which 2 shifts will get the extra nurses? The highest decimals, yeah. 0.64, that's the highest decimal, followed by 0.57. Those are the 2 highest decimals, right? Notice over here, this 0.50 is not going to be rounded up. That's different than Webster's. This one's going to go up to 72, and this one's going to go up to 45, the 2 highest decimals. The 49 won't go up, and even the 62 will not go up. Even though he was a 62.5, he did not go up because the other 2 decimals were higher. 0.57 was higher than 0.50. And we only had 2 extra nurses to give away. So those 2 decimals, the highest 2 got them. That's Hamilton. So Webster would have rounded all the 0.5s up, right? Little different. Good there? Good with that? Questions? Okay, number 6. A mother found an open box of her children's favorite candy bars. She decides to apportion the candy among her 3 youngest children according to the number of minutes each child spent doing homework during the week. That's not a fair reason. No, all right. Suppose there were 11 candy bars in a box. Given that Cindy did homework 54 minutes, Bobby did it for 2:44, Mary for 8:02, 11 candy bars, portion 11 candy bars among the children using Hamilton's method. So we're going to do Hamilton's method for these candy bars. I've got not much time, so I don't know if I want to do the whole Hamilton's method. Do you get the idea here that they're basically saying, who's first? Cindy. So basically we have Cindy, she did 54. It's like population, except it's minutes of homework. 50 for Cindy. Bob did 244. He's trying to show off. 244. Mary did, Mary really worked hard. Mary did 802. Maybe Cindy's just lazy. Okay, 11 candy. So there they are. They're the minutes. 11, the more homework you do, the more candy bars you get, basically, is her plan. So how's she going to do that? Well, we got to have the total. What's the total of all those? 54 plus 244 plus 802. I'm messing up my calculator here. Here we go. 1,100. 1,100 minutes. And then the standard divisor. Remember, it's total population, or total minutes, in this case, 1,100, over 11 candy bars. Candy bars are like the seats. The kids don't want seats. They want candy bars, right? Divide that. That's a nice clean 100, isn't it? So that's my standard divisor. So that means go back now and divide all these by 100. That's easy. So what do you get? Well, 0.54 and 2.44 and 8.02. And then what is we're doing Hamilton. What does Hamilton say? Hamilton says round down at first, and then give the extras to the highest decimals. So round down. What's 0.54 rounded down? What's 0.54 rounded down? It's 0. Cindy's going to wish she did a little more homework. 2.44 rounded down is 2. Mary runs down to 8. So if we give away 0, 2, and 8 candy bars, how many candy bars is that? 10. And we actually have 11 to give away. So somebody gets an extra candy bar. Who gets the extra candy bar? The highest decimal. 0.54 is higher than 0.44 or 0.02. So this one will go to 1. So Cindy's happy. She gets a candy bar. Bob gets 2. Mary gets 8. There's the 11 candy bars. That's what it says over here, right? Cindy gets 1. Bob gets 2. Mary gets 8. Now, here comes the trick. Part B. Suppose that just before she hands out the candy bars, the mother finds 1 extra candy bar. This is good news, right? An extra candy bar. There's 12 now. She found an extra one. Using the same method, now so if you do the whole thing again, but you do it with 12 candy bars. I'm not going to do it. We don't have time. You can see right here. You can write them down. It's going to be the same exact problem for you if you want to write them down. Look at the answers. Look what Cindy gets now. Now that we have more candy bars, nobody did any more homework or anything. It's all the same minutes. We're just breaking up more candy bars now. Cindy gets less. You know what that is? That's the Alabama paradox. That's exactly how Alabama felt. Like, how can you have more to give away and I get less? What kind of bogus method is that? Hamiltons can do that. Hamiltons can do that. Cindy gets no candy bars now. Which paradox? There it is. That's the Alabama paradox. That's exactly it. Next time, but they're not in the homework. They'll be on the practice. And we're doing practice exam next time, aren't we? So we've got to do that. Yeah, clicker quiz coming up. Let's do that. Clicker quiz. All right, quiz. There it is. Okay.